Hi, everybody, and welcome back on our discussion on data analytics. We're going to follow up to a recent segment that was posted regarding the multiple linear regression framework in matrix form. And what we're going to do in this segment is we're going to talk about something known as the pseudo-inverse estimator, which is a very particular solution to the problem of ordinary least squares. That's minimizing the sum of square residuals, but in matrix form. The pseudo-inverse estimator represents what we refer to as a one-step learning solution. It is an analytical solution to the calculus problem of minimizing the sum of square residuals. And I really think in this regard, understanding the optimization process working behind OLS, which is generating your optimal betas, understanding that process is really the key building block to doing, I think, most of machine learning. So I would argue that the linear regression framework is the first kind of key building block or key foundation in building up the framework to understand more complicated machine learning techniques in the context of optimization. So I want to just jump back to what we had seen last time, which was the ability to write out the entire set of regression equations for every observation more compactly in this matrix form. And what we're going to do in a moment is we're going to formalize the OLS problem, the sum of the square residuals that we're trying to minimize by choosing the beta vector here as our parameter estimates using this notational form. Now, before we do that, I want to talk just a little bit about the dimensionality of our regression equation in matrix form. Note, in the following equation, I've included the dimensions of each matrix or each vector in the bottom right corner outside of the square brackets. So the y vector, for example, has n rows and 1 column. The x matrix has n rows and k plus 1 columns. The beta vector has k plus 1 rows and 1 column. And the vector of residuals u has n rows and 1 column. And there's a really important fact. We discussed this before in a previous segment, but anytime we multiply two matrices together, the matrix on the left must have the same number of columns as the number of rows in the matrix on the right. Okay, so the columns of the matrix on the left have to equal the number of rows for the matrix on the right. Note that when we multiply the X matrix here times the beta vector, okay, this is absolutely a legal operation for us. Okay, the matrix on the left, the X matrix, has k plus 1 columns. The beta vector has k plus 1 rows. We can see that here. Okay, the other thing that we can see is that the product of the matrices X times beta has dimensionality of n by 1. Okay, and you can see that by looking at the outside numbers here. N is the number of rows in the X matrix. 1 is the number of columns in the beta matrix, okay, or the beta vector, rather. And that should make sense because when we add that result, X beta, to the residual, that gives us Y, and the residual is n by 1. And you cannot add two vectors unless they are of the same dimensionality. Before we move forward, I want to talk a little bit about another matrix operation, something known as the transpose or the transposition. And when you take the transpose of a matrix, what you're essentially doing is you are swapping the rows and the columns. So we're going to consider a 3x2 matrix A, and we're going to look at its transpose, which is a 2x3 matrix. And we use the T superscript here. It looks kind of like an exponent. It's not. It just means it's a transpose operation. And some textbooks, some notation, you'll see an apostrophe or like a prime used there instead. But I'm going to use that capital T superscript. And here's an example of taking a transpose. We have this matrix A on the left, who has a row of 1, 2. Second row is 3, 4. Third row is 5, 6. And then when we take the transpose of that matrix A, you'll notice now the first row, 1, 3, 5, of A transpose, that was what was the first column of A originally. And the second row of A transpose was what was in the second column. of A originally. So if you compare A and the transpose of A, the rows have switched roles and the columns have switched roles. If we were to do this to a vector, we could think about turning a column vector into a row vector, or even vice versa. So here's a situation where A was a column vector, it was n by 1, and now we took the transpose of A, and the result is 1 by n, 1 row, n columns. You'll notice sometimes it's more convenient to write vectors without commas in between each of the elements. I also kind of switched notation to square brackets here to be consistent with some of the other notation that I've been using. The last property we're going to use, and there's just one step in an advanced bit of material here that's somewhat optional. If we take the transpose of a matrix, or rather the transpose of the product of two matrices, then we wind up with the following result. So if we take the transpose of the product of A and matrix B, then that's equal to taking the transpose of B and multiplying that on the left of the transpose of A. And we're going to see that fact used in our OLS derivation in matrix form in a moment. Before we do that, we're going to talk about the objective of ordinary least squares, which is to try to minimize the sum of squared residuals by choosing the optimal parameter values for the beta vector. So this can be a big problem if we have k variables on the right-hand side of the regression. There's k plus 1 parameters that we're going to estimate. So we're trying to figure out what are the optimal values of those k plus 1 parameters that minimize the sum of the squared residuals. In the context of ordinary least squares, the sum of square residuals is what we refer to as our cost function, or sometimes referred to as our loss function. And the loss function, what that does is it measures how poor our fit is in sample. This is actually a measure of what we're going to start referring to as the in-sample error for the linear regression model. And the way we're going to estimate the betas is to try to minimize this in-sample error measure. Okay, we're going to try to minimize the cost, the sum of the square residuals, and we can formally state that problem as a calculus problem, as an optimization problem, where the subscript beta here is the choice variable. Okay, C of beta is the cost function. And then the way we can calculate the sum of the square residuals is just taking U dot product with itself, or U transpose times U will be the same thing, okay, which is again giving us the sum product up here, the sum of those squared residuals. So we're going to revisit this in matrix form and do a little bit of advanced matrix calculus. It's optional, but I want to put it out there in case anyone's interested. So we're going to revisit here how to calculate the residuals. Remember, for a given regression equation for a single observation, okay, we can solve for the residual. We can isolate U hat I here. So we can solve for that residual. And if we do that, we can write the residual in terms of this fitted value Y hat. And recall the fitted value was just equal to all the values on the right side of the regression, but not including the residual. Okay, so that was the equation of the regression plane or regression surface, or in the case of just one regressor, the regression line. Okay, in matrix form, the residual vector we can solve for using our matrix form regression equation. Okay, and now we can go back and revisit the formalization of the optimization problem here. So this part you don't have to worry about. I'm not going to test you on these steps in particular, but you should understand in general what's happening, that we're trying to figure out the optimal betas that are minimizing our in-sample error measure, which is the cost function, the sum of the square residuals. So we can go ahead now and substitute in for the u's y minus x beta. And the next thing we're going to do is we're going to do a little bit of algebra. We're going to essentially FOIL these two terms. And that is going to give us this messy result here. So let me just take a moment to explain. So if we took the two y terms and we multiply them, here's a y, but notice there's a transpose there. That's going to become a y transpose times this y. That leaves us with this term in red here, y transpose y. Then if we go to the second term, okay, this x beta, and that gets transposed. Well, remember we saw when you take the transpose of a product, okay, then the order flips around. We get beta transpose times x, and then we're distributing that into y here. So that's where this y term is showing up in the red. Okay, the next term that we're generating here is from us multiplying the two outside terms. So here we have this y transpose again, and we're distributing that into x beta, which gives us this term. And then last but not least, we have a term that kind of looks like beta squared times x squared. We got two betas multiplied together, two x's, but not in exactly the same order. Again, that comes from us taking the second x beta times this first transposed x beta. And again, when we look at this first x beta, because that transpose is there, we have to flip the order of multiplication. This becomes beta transpose x transpose. That's this first term. And then we distribute that into x beta, and notice we have a plus here. Okay, next thing we're going to do is we're going to check the dimensionality of these two terms in red. Okay, and remember, beta itself was a column vector. It was a k plus 1 by 1 column vector. Okay, which means beta transpose is a 1 by k plus 1 row vector. Similarly, x used to be, before we transposed it, x used to be an n by k plus 1 matrix. Now that we've transposed it, it is a k plus 1 by n matrix. Okay? So if we multiply beta times x, we're going to wind up getting a 1 by a 1 by n vector. And then we multiply that result by a y, and y is an n by 1 vector. So it turns out both of these terms in red, if you check the dimensions very carefully, okay, both of those terms in red are actually a one-dimensional number, a scalar. Okay, not a vector, not a matrix. It comes out to a scalar, and that means they're both actually the same value. So we're going to go ahead and just double the first number and recognize that we have two of those same scalars there. And what we would do next, once we've written our objective function out, then we're going to apply our calculus. So how do you find the minimum or the bottom of a function, right? You take the derivative and you set it equal to 0. And that is known as the first order condition that characterizes the optimum. Okay, so I want to just take a moment and talk conceptually about what we're doing by going back and thinking about a situation where we have just one x variable, which means then we have two beta parameters to estimate. I have the intercept and I have the slope. So we got beta 0, we got beta 1 to estimate. Okay, what we are doing conceptually here, when we take this first order condition, we're taking the derivative, the slope of that cost function, and we're setting it equal to 0, but we're doing this with respect to all the different beta dimensions, beta 0, beta 1, so on and so forth. But in the case where we only have beta 0 and beta 1, just one regressor on the right-hand side and an intercept, okay, this problem can be drawn in 3 dimensions. All right, so note the vertical axis, what we're measuring here, f of b0 and b1, that is the value of our cost function that we're measuring on the vertical axis. So that is c of the beta vector. Okay, similarly, this blue function that I've kind of drawn here in a sort of an odd way, it should look like a 3-dimensional bowl. And I've drawn those somewhat concentric rings to kind of capture how that shape of that bowl looks as we move up the cost function axis, up that vertical axis. Okay, so that whole blue 3-dimensional function, that is a bowl, and our goal is to try to climb to the bottom of that bowl by choosing the right combination of beta 0 and beta 1. So you see that red X kind of marks the spot over here in the beta 1, beta 0 plane. That is identifying the value that would put us right at the bottom of this bowl. If we move to some other value of beta 0 and beta 1 and then went up, we would wind up moving higher up on that bowl. And our job is to get to the bottom of the bowl. We want to minimize the cost because the cost is a measure of our in-sample fit, our in-sample error. Okay, so what we're going to do here to identify the bottom of the bowl is we're going to take the derivative and set it equal to 0. Now, because we have a three-dimensional diagram, right? If you think about climbing into the bottom of a bowl, if you're in the bottom of a valley, okay, how do you know you're at the bottom of the valley? Well, if you walk in any direction, okay, you're going to go up. Okay, and you would have to check not just one, but you'd have to check two directions, right? You'd have to walk north-south, and you'd have to walk east-west to check that for sure you were in the bottom of the bowl. So that's what we're going to do. We're going to take the derivative in the B0 direction, and that gives us the value. So we're going to set the derivative equal to 0 in the B0 direction, and then we're going to set the derivative equal to 0 in the B1 direction. And once we do that, we're going to look straight down, and that identifies where X marks the spot and tells us exactly what our optimal parameter values are that minimize that cost function. Okay, so that's conceptually, in my opinion, the root of all machine learning, is that there is some cost function. It varies from algorithm to algorithm, from model to model. Okay, but the general idea is we need the computer to help us calibrate these beta parameters by generally solving this optimization problem that is reducing the cost of fit. And we're going to talk about a lot of trade-offs involved using some advanced methods in the scope or context of this optimization problem. Now, before we get back to the first order condition, let's go ahead and we're going to take a little bit of a hiatus and talk about the inverse of a matrix. So we're going to consider here a square matrix A, and the inverse of A we're going to denote using this -1 superscript is the inverse of A. And the inverse of A, if we take the inverse of A and multiply it by A itself, this gives us something known as the identity matrix, which kind of looks like a 1. Right? If you take 3 times 1 over 3, the inverse of 3, you get 1. This is very similar. Okay, now computing the inverse matrix is not a very easy thing to do computationally, so we're not going to go through how to do that in this, this segment. Rather, we're going to leverage the computer to do that for us. We're going to use R to do that for us later on when we go through an example of how to implement the pseudo-inverse estimator in R. Okay, now again, that matrix I, this is known as the identity matrix, and it behaves similar to the number 1, but with respect to matrices. If you take any matrix and you multiply it by the identity matrix, you will always get back the original matrix. Okay, so the identity matrix is like the number 1 of matrices. Okay, and the form of the identity matrix, it has a 1 along the diagonal. It's got all 1s along the diagonal from the top left down to the bottom right, but not across, not from the top right also to the bottom left, just from the top left to the bottom right. And everywhere else there are zeros. Okay, and if it turns out this matrix has this nice property where if you multiply it by any other matrix, anything times I always gives you the original thing back. Okay, so it's kind of like multiplying by 1. There are also left and right inverses that may exist for a large class of non-square matrices, but this is also somewhat outside the scope of our current context. And if you're interested in that, definitely pick up a book on linear algebra. Okay, now I want to jump back to where we had left off, and that was analyzing this first order condition of optimization. Okay, so we got to this point using some matrix calculus. In fact, let me just jump back for a moment so we can see where that came from. So we can see here in this very last line, we've taken the derivative of the cost function. And in the line directly above, here is the cost function. We've taken the derivative with respect to beta, and it's a partial derivative. Meaning if there's a term like y transpose y, which is going to give us some constant value, and there's no beta in there, the derivative of that with respect to beta would be 0, right? The derivative of any constant like 3 or 10 with respect to a variable is going to be 0 because it's a constant, it doesn't change. You'll notice this term over here, we have 1 beta in it, right? There's 1 beta. So if we take the derivative with respect to something with just 1 beta in it, with respect to beta, that beta goes away. So this beta cancels here, and we're left with just -2x transpose y. And this last term looks almost like we have a beta squared. We got beta transpose and another beta over here. Kind of looks like beta squared. And hopefully you remember your power rule. If you have beta squared, The 2 comes out front, you lose one of those betas, becomes beta to the 1 power, and that's what happened here. This 2 comes out front from the beta squared, from this quadratic form, and we're left with just 1 beta as our first order condition. So we're going to go ahead and we're going to simplify that first order condition a little bit here. And the first thing to note that we can simplify is we can divide both sides of the equation by 2. Okay, so if we divide the left by 2 and the right by 2, the right's already 0. So 0 divided by 2 is still 0. That's fine. And then we can take the negative term. We can move it over to the other side here, make it positive, and we wind up with the following. And our goal here, just to keep in mind what that is, our goal is to solve for beta. So we want to get beta alone using this optimization condition. And the way we're going to do that is essentially we have to divide through by this x transpose x term on the left. That's what we're going to have to do. Unfortunately, you can't divide in matrix algebra, but what we can do is we can multiply by the inverse matrix of x transpose x. Okay, when we do that, okay, the term in blue here is an inverse matrix times the original matrix. And hopefully you remember, because we talked about it just a moment ago with respect to our hiatus on inverses, that when you take the product of A inverse and A, this gives you the identity matrix. And anything times the identity matrix, right, I times beta is just beta, which means we have solved the optimization problem. We found the choice variable's value, right, the value of that vector beta, and that minimizes our cost function, that minimizes the sum of square residuals, which was a measure of our in-sample error. So this solution here that we've figured out, this is known as an analytical solution. There's an actual formula that we can plug our data into, and boom, we can calculate the beta in 1 step without needing some sort of iterative process that we have to feed to a computer that has much more unlimited capacity than humans do. So this is a beautiful result in that regard. We don't necessarily need an iterative learning algorithm to solve this climbing to the bottom of a bowl problem. Okay, we can use the pseudo-inverse matrix solution here for beta star. We plug in X, we plug in Y, right? We plug in those matrices and vectors, and boom, we can do this calculation and we can get beta star. We're going to show you how to do that in another segment in a moment in R. So we're going to come back to actually implementing that in a somewhat real framework. Again, in machine learning, we refer to this particular solution for the linear regression model. That is the solution to minimizing the sum of square residuals, minimizing our in-sample error. We refer to that solution as a one-step learning solution. We plug in the values into that formula, and that formula was giving us an analytical solution here. An analytical solution meaning we can write out an expression for what that value is algebraically. There are many cases where that is not possible. For example, if you take the equation x cubed plus 2x plus 4, it's probably very difficult to find an analytical solution if we were to set that equal to 0. Okay, it's a cube, there's some square term in there, it's kind of awkward. You could solve it with a computer, but there's not a written open solution, or rather a closed form solution, an analytical solution. Now, why do we call this the pseudo-inverse solution? Well, part of the solution is known as the pseudo-inverse matrix, and that is the component where we have x transpose x inverse times x transpose. That is known as the pseudo-inverse matrix. And if we were to take the pseudo-inverse matrix and multiply it by y, the data values for our output, okay, that is how we would recover the optimal parameter value. So again, this is an analytical solution. Okay, this equation provides us with an analytical solution, a closed form solution to this problem of minimizing the sum of square residuals in the multiple linear regression framework. Okay, and the way we get that is by calculating the pseudo-inverse matrix. which requires really only the input matrix X, right? We take X, we transpose it, we multiply it by itself, we inverse it, we transpose it again and multiply it by that. And then we multiply that pseudo inverse by Y. Okay, if this sounds a little daunting, I think once you go through an example, you'll see it's actually fairly straightforward. Once you have your data organized in the X matrix and you separate the Y values out into the Y vector, it's really one line of code that does this for you. And the important thing to see here is really understanding what is going on in the background when you're using a software package that implements some sort of machine learning algorithm, like regression. Or specifically, even if you're only implementing regression, it's important to understand what's going on underneath the hood. So some of that, rather technical, apologize for that. But again, you do not need to, no, it's not mandatory to go through that derivation of the OLS estimator, but you should know the form of the analytical solution. You should be able to apply that. But I will not make you on an exam derive that using that matrix calculus. Stay tuned for more. Next on the agenda, we are going to implement the pseudo inverse estimator in R. Stay tuned.